Hey, George, you're a scientist.
I'm a chemist, yes.
Right, you're a scientist. So, we've been talking about a bunch of like summery, temperatury things. And one of the foods my kids love to eat in summery time is fruit, which is nice because it gives me a break from buying freeze dried fruit, which is the thing my younger daughter eats way too much of. And I realized, like, I know those words. I know freeze, I know dried, and I know fruit. And so, like, separately, I feel like I understand more or less what's going on. And yet, dried fruit is nothing like freeze dried fruit. So, that freeze is doing like some serious heavy lifting to the end product you get when you freeze dry as opposed to just dry something. So, I guess at the risk of massively overcomplicating something that may be simple, what the hell is actually freeze drying?
Well, darn it, Lions, I'm a chemist, not a fruit expert or a preservations expert, but with my very limited knowledge and very limited expertise, I will attempt to opine to this. Speaking of, though, do you want to know another name for freeze drying stuff?
Is it like a cool science name or is it like a weird
is.
industry name?
It's a cool science name.
Ooh, what is the cool science name?
Cryodesiccation.
That sounds violent.
Right? Well, and when actually, if you break down the word, right, freeze, cryo, drying, desiccation, like it's the same exact, like, you know, antecedent and suffix, but like, I don't know, man. If you said like, oh man, I'm gonna freeze dry that fruit, you'd be like, all right, no, it sounds good. I'm going to cryo desiccate that fruit. You'd be like, that costs.
Yeah,
when you do it that way,
fruit do to you?
It's the exact same process. It just costs 10 times as much.
Yeah, it's scientific.
Absolutely. Yeah, just like the I don't know if we've ever shared this one online, but I still remember at one point we had special Q-tips that we would use to clean like the source for a mass spectra, and you know, whatever, a thing of a million Q-tips cost like $3. A bag of 50 of these cost $50 because they were super scientific. And we just started getting the cheaper ones because they're the exact same product. And it was, yeah, anyways. So I say all that to say cryodesiccation. So with that in mind, let's talk about something else for a minute. So
whoa, a tangent between us? Unheard of.
Yeah. Unspeakable. So let's create a list and let's see if you can get on the list of one thing I'm looking for, because there's a lot of things. So, what are the main things that life, or bacteria specifically in this case, need to thrive?
Okay, so I think all life that we know of needs carbon, needs water.
Mm-hmm.
I think all life needs oxygen, but I don't think they all get it in a way that's like recognizable to us, because isn't there like anaerobic bacteria around like vents in the ocean that like they still end up getting the like stuff they need out of it, but they are in an environment that does not have like oxygen in like a form like fish could use or we could use.
Yes, it is my understanding that anaerobic bacteria do not require oxygen in order to survive
at all. So they're not like getting it out of some other source.
To my knowledge, is that like basically the problem with anaerobic bacteria is that they can continue to thrive in areas where there's not a great air exchange. So that's why like you end up with it in like like cans and stuff like that, and like botulism, if I remember correctly, is a type of anaerobic bacteria, which is why it was so problematic in canned foods.
Gross. Okay, so water, carbon.
Again, not a biologist. Don't quote me on that.
Water, carbon, some kind of energy source, right? So like food, essentially, right? Like you have to consume energy from your environment. I mean, I feel like I could list more things, but they're starting to feel less fundamental than those things.
And more importantly, you got the one I was looking for. So basically is that, yes, they absolutely need food. They need something to build with themselves, but also they need water. What do you like, why do they need water? Because this is kind of the interesting thing.
I mean, it's a like fundamental part of the structure of a cell, and it's involved in like lots, there's so much chemistry. So many chemical processes rely on the presence of water, and I think that's what makes it required, but that is part of what makes it required anyway.
Yeah, you're certainly directionally correct. So basically, is that like, yes, all of the chemical reactions are based in an aqueous medium. Very few are based in a organic medium. So nailed it on that one. But more importantly, is that like it allows for fluid exchange and chemical exchange, right? You know, so like when you think about how many units of stuff you have per unit volume, right? Water or a liquids are the most dense, while still having the most free-form movement, right? So water...
So things can pass freely kind of through water.
Correct, yeah. So like, for example, if I excrete urine into if I sit myself into a 55-gallon drum of dirt and then pee, me and that pee are just going to sit there forever until... right? But if I pee in the pool, right, eventually... that becomes not my problem. It becomes everybody else's problem, right?
If I was keeping a list of the ways you have had to try and explain scientific concepts to a layperson, that one would have just instantly become a contender for top.
Right. So the thing is that when you're peeing in the air, right, you know, like it just kind of goes, it goes everywhere. There's not a medium to hold it and carry it away so much. It just kind of goes until it hits either water or earth, and then if you pee into solid, right, if you excrete into solid, it doesn't go anywhere, you know. So you need some medium to exchange different chemicals, right, be them waste or food or whatever, right, and especially bacteria. Like we're able to move around because of the incredibly complex series of chemical reactions and cells and all that kind of stuff going on in our body. But most cells only can move in water, right? Because they have the little, you know, cilia that let them move, or the flagella that lets them move through, right? You know, so and that's also very critical because they need that in order to procreate, in order to divide, right, and in order to thrive. So, okay, done talking about that for now. Now I just want to talk about water for a little bit. And it'll all come together. So this is definitely one of the things I really love about this show is it allows me to kind of shave off some of the weird blind spots that I have, you know, in my chemistry knowledge, because it's one of those things where it's like, oh, I remember learning that once. And then when somebody asks you, hey, do you remember the water phase diagram? I'm like, yeah. And then like, can you draw it for me? No. So
your second question was different than your first question.
So let's play a game. Let's play the game of, can you name all of the different names for all the different phase transitions for water?
I mean, like in layman's terms?
Well, no, so for example, when water goes from a liquid to a solid, we would call that
freezing.
Yeah, so you already got one. There's only 6.
Yeah, but I didn't know if there was some insane Latin term.
Oh no, it's just freezing. Yeah, but they each do have a name associated with them.
Yeah. So you would have, let's see. So solid to liquid then would be melting.
Yep. Got those
liquid
two. Good.
To gas is evaporating.
Oh, you're really close. It's vaporization. So
crap.
Yeah,
right. Because it's, what do you get? Water vapor. So it's vaporizing. Which is another term that sounds like way more violent, right? Like if you said, oh, I can tell that the pot is ready for me to put the pasta in because the water is vaporizing. Like, that sounds so intense, right? Because we associate that with like, he got shot with a laser pistol and he was vaporized.
Which is interesting because when you shoot somebody with a laser pistol and vaporize them, that implies that they were liquid before, but they're not. So it's actually even the wrong word in that case, because they are going from solid to gas, which is a different thing.
Oh, so if you go directly there, it's not like you don't always have to drive on all streets to get to your destination. You don't have to go from solid to liquid to gas. You can go straight from solid to gas.
You absolutely can. Yep.
Okay.
There's a word for that.
I'm not sure I knew that. Like, I knew you could go from solid to gas very quickly, but I think I was just kind of assuming you technically pass through liquid, but I guess not.
No, you can go straight from one to the other. In fact, you have probably borne witness to this because when you throw a bunch of dry ice into a cooler, is there any water left over?
Oh, that's true.
Right. So, so that one does the solid to gas one. So you've gotten three. So you've already gotten 50%, right? You've gotten three of them. So you've got so the last of the ones I think you might know reasonably is what's gas to liquid. So you got liquid to gas is vaporization, right?
Yeah.
I can't count evaporation, vaporization, right?
Like condensation, like condensing.
Got it, man.
Yeah.
Yep.
Okay.
Now what are the other solid to gas and gas to solid?
Solid gas to solid. I know this. There's no way that this is right, but the word that leaps to mind is like coagulation.
Oh yeah, that's cool. That's not it, but I could see that.
Yeah.
Yep. So gas to solid is deposition.
Oh yeah. No, I'm not sure that I ever heard that.
Yeah. Well, and because if you think about it, it kind of makes sense because typically, like you've got, if you would be looking at it in an experiment, right, is you would have a gas that immediately goes straight to solid. It deposits itself on the surface, so it's deposition, because it's kind of what it would look like if you're doing an experiment where deposition was part of it.
Well, one side of my family has a lot of people involved in like law careers, and I'm never going to be able to hear one of them talk about depositions the same way.
Yes, when they gave their deposition, it's like, did they turn into a solid on the what happened there?
You mean like when Alucard goes from being a gaseous cloud to being Alucard again?
Exactly. So actually that's interesting. Yeah, so when he goes from when Alucard goes from being a gaseous form back to being a vampire, that's deposition. But what about when he goes from being a vampire to a gaseous cloud?
Well, it's not. It's. I want to say there's something with like the root word like volatile in there, like it's like volatilizing, like going straight from a solid to a gas. But I don't. This may also be one I've never heard before.
You almost certainly have not heard of this one. And you got the volatile one from like vaporization, volatile. Like that's because normally when you talk about things that are volatile, you're referring to a low boiling point specifically.
Right.
So that means it.
Yeah.
So it starts liquid and then volatilizes very easily. Sublimation is when it goes from a solid.
Oh, I know that word. Gas. I didn't know that that's what it meant, but I actually did know that word because you hear it in like science fiction, like like your actually now that I think about it, I've always heard it used with liquid, like your blood will sublimate or your saliva, but those are liquids.
Yeah, those are liquids. Those all vaporize, right? Yeah. So that's So and sublimate is one of those ones that like it doesn't have cause to be used for a lot, but it does make sense to be used a lot in sci-fi because of the instances in which we see them. So again, to kind of set the foundation a little bit more, so let's talk about what some of these phase transitions actually seem like, right? So when you freeze something, right, you're taking it from a liquid to solid. We see that all the time. What's something that generally? What is the thing that generally causes freezing?
Low temperatures.
Low temperatures, right?
Okay.
When it gets,
I was like, oh god, is this a trick question?
When it gets cold, and so basically what that means is, and as we've discussed, the temperature of a thing is a measure. Let's see if you remember this one. The temperature of a thing is a measure of
kinetic energy in the system.
You got it. Kinetic energy in the system, man.
Yay.
Yeah. So basically what that means is as it's freezing, you're robbing kinetic energy from the system. So that means that, as I mentioned before, all of these molecules are pretty close to each other, and they're kind of like rolling around each other because they have the kinetic energy to do so. As you start to steal the kinetic energy, they become more and more and more stagnant until they kind of lock into some low energy state, usually some sort of a lattice structure, right? If you're talking about water. Because it has to arrange itself in such a way to get its partial negatives and partial positives all pointing in the same direction. Also why it expands when it freezes. Melting, opposite way, right? So they all just don't have a ton of kinetic energy. They're locked into place, and then they start moving, and then they melt, right? Easy peasy. For vaporization, you go through typically boiling, right? And the reason why is because most, if not all, things on the planet Earth, right, have some type of dissolved gas in them, right? So as you heat it up, those dissolved gases start to, escape from the material and begin to boil up. And as you do that, it agitates it, and more air gets in, and so on and so forth. If my memory serves, I didn't double check that before I did that. But the most important bit is that when you think about vaporization, going from a liquid to gas, would you describe that process as calm or violent?
I would describe that as violent. I mean, all the words we use for even just casual things, like it was a rolling boil, right? Like it's heaving, like it's a lot of, at the very least, energetic words, if not violent words.
Right, exactly. So the thing is, it's a very violent process. So typically, is if you've got, it is the bull in the china cabinet, bull in the china shop, right, of phase transitions, where like it gets the job done, it'll get you into the gaseous state, but man, is it violent. And so if you were to suddenly try to boil off all of the water in the strawberry, what do you think would happen?
Oh, I assume you would end up with like kind of a horrible goo, like
just horrible mess.
So much energy in the system that it would do other chemistry, right, and other physics on the other parts of the strawberry.
Yep, absolutely. And also too is it would rip apart, like the cell boundaries, things like that, right? So then all of a sudden all of the cells insides become cell outsides, and you want to keep the insides inside if you want to continue to strawberry, because that's what we define as a strawberry, right? So basically what a bunch of people says, they said, man, all of this stuff, everything that we have would keep way better if there was less water in it. Why would it keep better if there was less water in it? Because that's what bacteria needs in order to procreate and survive. So if things are dry, they keep longer than things that are wet, like fruit. And so somebody was like, okay, so we can sit there and just try to desiccate the ever-loving hell out of it, which basically most of the time in a desiccator, what you're doing is you're kind of leveraging the idea that the universe moves towards entropy and chaos. Where so basically is if you've got one thing that has a lot of water and one thing that has no water, the water wants to even it all out. And that's basically what a desiccator does, right? And somebody said, that takes too long. So here's what I want to do, is what I'm going to do is instead of using vaporization in order to get rid of all of the water, or instead of using just time, I am going to use sublimation. So what they do is they actually freeze the thing. And so here's the interesting thing, is you'd say like, okay, well, they freeze it, but then they'd have to get it back up to water and back up to boil. You're going in the wrong direction, right? So what they do is they freeze it, but then the state of the matter of a thing, right, is based off of two factors: temperature and
Yeah.
No, you got this. I believe in you.
No, I'm trying to think the state of the, like, you mean whether it's solid, liquid, or gas?
Right, is dependent on temperature and
density.
Close. I think you're thinking of the right thing. Because when people talked about like the your saliva vaporizing outside of your mouth didn't get a lot hotter, what was the thing that changed in this sci-fi that you watched? Pressure, right, exactly. If you drop the pressure, then you can facilitate phase transitions, which I think is pretty neat. So basically what they do is they freeze everything, right? So now all of a sudden it's in this frozen state, and then they just drop the pressure, which then causes it to sublimate, and it all becomes gas. And because it's already frozen, it just leaves, because it just goes straight from solid to gas. So it just, where there was water, now there is nothing, which is why it also tends to be a lot lighter, and kind of like dissolves in your mouth, because it still has all of that sponge-like tunneling in there from where all the water was. So basically they lower the pressure, and then that does the primary drying, which induces sublimation. Then they do like a secondary drying where they move the temperature up a little bit to get all of the little bit that was still liquid water out. And that leaves generally a residual water content of about 1 to 4%, which is not typically enough for life to easily start forming in large quantities, which therefore preserves it.
So you may or may not know the answer to this, but when you said like, that takes too much time, the like sad middle-aged person who has a job so he can pay his mortgage in me was like, oh, right. And the more time intensive something is, the more it tends to cost. And then it's like, you get less value because it's hard. You can't make as much dried fruit if you have to dry it slowly in like an oven or, crucible or whatever. But freeze drying, we can do that super fast because we can freeze it quite quickly. And then we just put it in what I assume is a fairly sophisticated piece of machinery that allows them to create like a low pressure environment. And then as my brain was starting to step through that, I was like, that sounds more expensive. But I'm thinking you could actually make a rudimentary pressure vessel. Like, it's not that hard. Like, you just need something that's structurally sound and a pump. So
Yep.
maybe this actually isn't that difficult.
It's not super difficult. No, I mean, like, to your point, right? Is that like all you need is just a vacuum sealable container and a pump, and that's it. I mean, like, literally, they make kind of glassware that is very easily purchasable. Where you just there's like a lot of glassware where there's like the thing, and then there's the thing with 2 glass holes in it, and that's
yes. I can picture the background object in a science fiction show that you're talking about, right? Where it's like, oh, that's a beaker. No, that's the beaker with 2 weird holes in it.
Yeah, that's the beaker that we use to create a vacuum. Because like, there's also like, for example, an Erlenmeyer flask, which is the one that looks like a triangle, right? A lot of times, like, you have like a funnel going into that, and you can sit there and what's called gravity filter something, which is like what you would do with coffee, right? You're gravity filtering, or you just hook a vacuum up to that. Now you're vacuum filtering. Goes way faster, right?
Years ago, for one of my mother's milestone birthdays, my family got together and we took her to like a nice restaurant, and it was like courses, right? It was like big deal, like, oh, you're dressed up. And I had never seen a gravity filter coffee machine, and the one they had looked like a giant hourglass, and they came and set it on the table, and like, we're all like chatting and having a nice time. And then we looked back and realized that the urn that had water in it now had coffee in it. And that felt like a magic trick, right? Even though like the thing was in front of us the whole time, you could see exactly how it works because it's all clear glass. But that is why you can put colored liquids bubbling in the background of any science fiction thing, because apparently humans just look at liquids bubbling and go, whoa, magic.
Yeah, pretty much. Actually, this is definitely tangential. I was talking to a new hire that we have at work recently, and she is learning how to do chromatography. And I was like, "Are you familiar with chromatography?" And she's like, "I mean, I think so." And I was like, "Well, can you elaborate? Like, I'm on your time. What do you got for me?" And she said, "Like, I know it's not this. I know it's not. Like, it's in an attempt to like not insult me. She's like, I know it's not this, but like I know that like chromatography, like I think that was what they called when we like wetted a sheet of paper and we put a marker on it and then like the colors separated out." I'm like, yeah, that's chromatography. She's like, is that what we're doing?
You have to now just carry a couple of Crayola markers in your lab coat so that whenever somebody remembers that again, you can just be like, yeah, and like pull one out. See, you remember,
yeah, it's just kind of like,
this is a science tool. This is a scientific marker.
Yeah. Well, I mean, if it's a scientific marker, it costs 17 times more. And,
that would be like rose art, not Crayola.
Yeah, exactly. But yeah, she was like, is that it? Like, that can't be it, right? It's like, same in principle. And kind of the same thing here, right? Where it's just kind of like, what are you doing? Well, we're just freezing something and lowering the temperature. And it's just like, oh, well, surely there's more to it than that. No, not really. Just kind of scale, and rigor, to make sure you're always getting it to the same temperature and that you're always lowering it to the same pressure, which is giving you similar results and blah, 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 blah. But outside of that, it's like, no, man, you could almost certainly, if you put your mind to it, for maybe $100, pull together a freeze drying apparatus, less the pump. The pump would be pretty expensive, but
and this is the part I'm now thinking about, because I love jerky. I love dried fruit, not freeze dried fruit. I love dried fruit because it's still got some moisture, so it's kind of like chewy, leathery, right? Like I love it. It's very expensive, but it is a treat I will give myself once in a while. And you can, if you are patient and you are willing to spend the money, if you have like an air fryer or even just a regular oven, you can totally do that at home. And right now, there's a little part of me that's like, could I make freeze-dried fruit at home? Am I willing to have something that is under possibly explosive levels of negative pressure, like around my home and family?
Well, so the one nice thing, if you're to do, and obviously always do things safely, read the labels, don't hurt yourself and then try to sue us. But that being said, is that like the nice thing is that one, if you were to get the apparatus to do it, like I said, like if you've already got a vacuum pump for something, right? If you've already got that, getting the glassware to do it, most of the time the glassware that they give you, if you were to get the correct type of glassware, it's like rated way higher than anything that you would be doing with it. And also too, it would implode if it were to go sideways, not explode and throw glass shrapnel everywhere,
That's true, because negative pressure.
Yeah, because you're pulling pressure out of it, so it would collapse in, not explode out, So like
this you're talking me into this. We could do this.
Yeah. Oh, we totally could. The next time I'm visiting, and I'm picturing it now. I mean, you just put the pump on top of your refrigerator, right? And then you snake the line into the freezer, right? You put the fruit in there, and then you just leave it in there for for us, because we don't want to. We want to make sure, right? Just put the fruit in there, leave it in there for a day, then just come in, you just turn the pump on, right? And then just walk away for several hours, and then let it do its thing, and then we'll test the results, man. This sounds like a good experiment. We could get all the kids together. Let's do it.
Yeah, this reminds me of some other dangerous home science experiments I want to ask you about.